Hello, good afternoon. My name is Matt, and I am a network automation engineer at Facebook. The theme we had for the hackathon this session was traffic exceptions. So we know that traditional routing, we have prescriptive desired topologies, and we use protocols and costs to define desired traffic flows. We use BGP policy to express business logic as reachability, or we can use TE to add constraints to our path selection. Reactive scenarios tend to focus around link failure, and we try to solve how do we retain connectivity and capacity. So we have IGP reconvergence of constraint SPF, LSP signals over available capacity, and really all this work is to try to get back to our desired topology. But what if we could react to individual traffic flows? So there are three main components to handling traffic exceptions as I see it. The first is traffic triggering, and this is monitoring traffic flows and flagging those flows based on desired characteristics. We have network config, which is a config that exists on our network today that supports the desired outcome. For example, redirecting traffic or dropping traffic. And then we have traffic influence, which is the mechanism that connects the trigger to the config. You may think right now, yes, Matt, I'm already running this on my network. It's called DDoS. Or DDoS mitigation, sorry, not DDoS. So traffic triggering tends to be we detect attacks via rules or machine learning, a customer phone call. We have config, we have BGP policies with communities, and if we see prefixes for these communities, we drop traffic, or and we can influence this traffic based on BGP flow spec or remotely triggered black hole. But I really think that we could do so much more. In a reactive network, we have traffic triggering, like we could do more advanced things looking at malicious layer 7 API requests or counting TCP retransmits and doing further analysis, maybe using TTL as a source-defined priority. So if we have a TTL that comes in to our network of higher than 200, we send it around the scenic route. Or even doing more advanced things like encoding BGP communities and TCP option headers and doing intent-based networking. Network config, we can do things like network segments that attract traffic via BGP flow spec, and then maybe for our traffic influence, we use things like ExaBGP to provide an API to advertise these flow spec rules. Thank you. I'm going to now hand this off to our three teams, and they're going to talk about their demos.
Hello, good afternoon, everybody. We are Team CU Buffs from the University of Colorado Boulder. This is my team, Sadhvi, Parth, Sahana, and Akshay. Our hack was handling multiple HTTP requests that enter into the network in a given interval of time, and then rate limiting the traffic based on whatever is received. The key points of our hack were exception traffic, handling of exception traffic using ExaBGP, DSCP marking, and traffic shaping. For traffic monitoring, we used Twilio API and Freshdesk. For failover handling of traffic, we used route manipulation. And for traffic visualization, we used Grafana and Matplotlib. This is the rough flow of our hack. We would sniff and analyze any traffic that enters into our network. If the traffic crosses a certain threshold, the HTTP request, we detect the source of the traffic using SCAPI and send the traffic for monitoring a visualization. And at the same time, using ExaBGP, we inject a route into a network. And after injecting the route, when the traffic comes in, we rate limit the traffic. Over to Sadhvi.
So we live capture traffic exiting host 1 and periodically transfer this to our sniffer using cronjob and rsync. The sniffer then analyzes this traffic to identify any exception traffic, which we are defining as a bunch of HTTP requests from a single source which is exceeding a certain threshold. When this is identified, the sniffer then notifies the ExaBGP to make config changes into our topology to handle these exception traffic. The XBGP, to notify the XBGP, we initially tried using netmiko, which SSHs into the XBGP, makes config file changes, and then the XBGP process is restarted. Since this wasn't super efficient to do every time we needed to change configs in the topology when exception traffic was identified, we opted for the secure API, which leveraged XBGP's existing API to make config changes without having to actually restart the XBGP process every single time. Over to Akshay.
Thank you. Whenever the XBGP API is called, we will inject a route on the R2 router. So we use FlowSpec for this, and we use FlowSpec because we can match on source IP, we can do destination IP as well as the layer 4 headers. Once R2 gets this advertisement from XBGP, it will propagate this information in its BGP network, and R1 and R4 will know about this. The best part of it is that we have marked this particular route with a DHCP value of 10, and we use a policy map to throttle this traffic on R1. This is because whenever there is a failover on R3, we will have all the exception traffic as well as the good traffic flow from the only path via R2. So whenever there is a congestion, we need to throttle the exception traffic and we need to let the good traffic pass by. We attract all the exception traffic to R2 using a higher local preference. Over to Sahana.
Apart from detecting and handling the exceptions, we felt the need to visualize the traffic. So we kept account of packets that were responsible for the exceptional traffic on the sniffer itself, and we pushed it into a database which was hosted on sniffer. We used Python's own matplotlib library for this graph. We also pushed it into Grafana for further visualization, and this is what you can see there. Over to Parth.
Thank you. Another major component of the hack was to do the notification. Like, we don't want NOC people to not know about it. So we use a tool called Freshdesk, which what it will do is, like, whenever there is a traffic exception in our network, it will just raise a ticket on this tool, and network admins can just work on it, and they will get notified about it. But this is not efficient. So we used a Twilio API, which will do a live, a real-time call to the network admins, and it will notify them yeah, there is a traffic exception in your network from this particular source, and this type of exception has occurred. So we use the Twilio API for that purpose. There are a future scope for the project. We can definitely scale the idea for a higher level of networks, a production grade networks. And we can since in our hack we just use HTTP traffic as our exceptions, we can use DNS or jumbo frames as an exception traffic as well. We can definitely make use of this application to have IDS or IPS or traffic backhauling mechanism in our network. Some key takeaway from this hack was we got exposure to many different new tools like XBGP and Twilio APIs. Teamwork and time management was definitely a big part of for this hack to be successful. We would like to thank all the sponsors and all the mentors for helping throughout the hack, and especially our professor, Dr. Levi Perigo, for helping us for the hack. And we would like to thank Nanook for giving us an opportunity. Thank you.
All right. Hey, everyone. I'm Zoe Blevins. I'm with Netflix, and I'm here with David Testa from Verizon Media, and Tony Franklin and Kyle Bean from Ball State University. Our team name was Pod 1 because that's the pod we were assigned, and we're really creative. So I'm just going to start with so basically what we did is we created just a bit of operationalization on top of the existing demo that Facebook opened with as part of the hackathon. So just a quick overview of what the topology was at the start. So similar topology to what you guys saw from the previous team. But we had a sniffer running attached to router 1 that was detecting, using Scapy to detect traffic coming through that link. And it had some rules set that if it detected a certain number of retransmits through that script, it would forward some rules to XBGP over an HTTP API. And that exabgp rule would reroute traffic through router 2 into what we called our analysis segment, where there might be other tools hosted that could then analyze that traffic further, look for trends, et cetera. So just a quick overview of what we did. Rather than having the rule immediately forward data to exabgp, we actually had it send all data that it analyzed to an API. And then in the cases that the retransmit threshold was exceeded, it went ahead and alerted, sent a Slack notification to our team channel. And then we just tossed up a quick HTML and CSS front end to get the status and to manually redirect that traffic when it was desired. So I'm just going to give a quick demo of what this looked like. So on router 1 and router 2, the initial state, we didn't have any routes in the flow table. The sniffer ran, and for the purposes of the screenshots here, this was just using a pre-existing PCAP, but this actually also works live on the wire. You can see for every packet that it processed that it sent a status message to our exabgp-based API. And then as soon as the retransmit threshold was hit, which was in this case 5, it sent a notification to Slack and continued to send data to the API. So this is what the Slack notification looked like. This is actually 1 per run, so it's not going to send a message every time the threshold is exceeded, only the first time. And then if you were to click into that Slack notification, it would take you to this front end. From here, you could decide whether or not you wanted to announce the redirect to exabgp to send the traffic to the traffic analysis segment. So if you were to click that announce redirect button, you would get these commands executed to the exabgp process. And then if you were looking at the exabgp process output, you could see the flow added messages. And on the router 1, you could see the new routes in the flow table. Same on router 2. From there, you may choose to withdraw that announcement, withdraw that redirect. You've got the data you want. You want to go ahead and turn off that redirect. So you can hit the withdraw redirect button. Commands execute again. You'll get the withdraw flow route messages to exabgp. Same messages on from the exabgp process, this time removing. And you can see those routes have been cleared from the table. So just a quick overview of how we did this. So in the original detect retransmits Python script, it was calling exabgp directly as soon as the retransmits occurred. We added several APIs to the original API, so to accept status data, to display status data, and to allow for programmatic announces and redirects, or announces and withdrawals, rather. We added a front end. It's literally just HTML and CSS. I really didn't want to write JavaScript, but it could be a lot prettier with some JavaScript. And on the exabgp process, this is probably the most technical change in that we really wanted to be able to run this on port 80 so we could easily access the UI without having to do SSH tunneling. And so we actually separated out the API from the exabgp process. And so it's running in USG. And the bridge between USG and the exabgp process is a named pipe. Exabgp already had native support for that, but it wasn't quite working in our case. So we added a process within exabgp that was tail-effing that named pipe and then getting the messages standard out that way. So obviously, there's a lot of ways this could grow. Some JavaScript would be great to sort and filter that table. If you run that detect retransmit script without the PCAP as input, it gets all the traffic that's on the wire. And what's really fun about that is if you don't add in any filtering, every request to the API creates a new flow on the wire because it's all within the same network. So you get an infinite set of packets that are being forwarded to the API, which it handles just fine because this is all within a local network, but not something you would want in production. Obviously, we would want the ability to customize what our exabgp actions are, so you could have more advanced forms than just clicking a button. We could get confirmation that those commands actually resulted in router changes by setting up either polling via CLI, via GNMI if it's available. That kind of functionality could exist to just show the success of the commands. And obviously, it would be good to detect traffic anomalies other than retransmits. So that's our project. Thank you.
Good afternoon, everyone. So I'm Soham from my team Path Tracers. Unfortunately, some of the folks are not here with me currently, so I'll get started. So what we had is, we had like 2 sub-teams within the main team. One of them was trying to look at how we can address ECMP and traceroute issues together to get a better data from a traceroute when we do ECMP. And another was working on the Facebook hack, which was analyzing the flow and determining a better traffic flow for IGP, BGP, as well as custom traffic drain if required. So what we eventually wanted to reach a stage was if we can run this custom traceroute and find the hop which does not give back the data we need, and then we can analyze that link and then basically take it out of the network. But we couldn't complete the integration at the end. So yeah, the context was to be able to investigate routes which have ECMP and then be able to influence the link state, the underlying IGP for the same, and then being able to automatically respond to route traffic through some other path. We use Napalm for as a centralized service to collect data for the interface and the link stats. We took a approach we basically investigated Paris traceroute, which kind of uses TCP and UDP for checksum and sequence numbers and plays around with it to get better data for the normal traceroute which we have. And we also came across midway through the hack about the Facebook FP Tracer tool. And we tried to then work through it and identify what we can do better by using both of these together. So our first attempt, like I told, was to understand Paris traceroute, which is written in C++. What we wanted to do is write it in Golang. And we began to kind of implement it using UDP. And then we discovered that FB Tracer has already this mechanism, but it does using TCP. So our second attempt was if we can use Golang using concurrency and Go routines, and then get a logic to kind of test various TTLs. Some of the things which we wanted to add was UDP and ICMP data, and we also wanted to build a CLI utility rather than a library. So we kind of forked the FB Tracer version, and we tried to add whatever we can. This is the first part of the hack. So here are the results which we got. It's not clear, but basically we were able to get some better data out of the current FB Tracer utility for multiple AS numbers and some of the source addresses. So on the left side is the one which is currently was there, and the right side is the one which we tried to fork and get some data, better visualization for the same. Next, we wanted to influence traffic for the current FB hack. So we tried to use the sniffer service and run a health check service of sorts, which would basically combine with the sniffer and identify traffic paths which can be used in case we hit a scenario wherein the alternative path has been taken, but the alternative path, some segment in it has taken some errors. So what do you do in that case? So we identify the rogue link, we run the health check service which I mentioned, and we look out for interface errors, flaps, or utilization. Based on it, we try to drain it by making the IGP cost as high as possible so that the underlying IGP doesn't prefer it anymore. So this was kind of a traffic flow. Let's say R1, R3, and R4 is the normal flow. You take it, basically you use the exception traffic to make it go through R1, R2, and R4. However, let's say you have consistent flaps happening between R2 and R4. You try to mitigate it as far as possible, but you're still hitting the same error because your production traffic is going to take a hit if there's a flap. So this is what we try to do. We kind of continuously maintain a state using Napalm for the interface. And if we have a custom defined threshold, we had a 300 second for this one. So if it is last flap before that, what we try to do is we log in and make the IGP cost as high as possible so that a lot of traffic then goes and reroutes, even though it's a less preferred path, but at least the packets won't get dropped. So here's the interface where we try to kind of flap it and then run a manual test for it. So we increase the metric over here. We use OSPF in the current hack. In terms of learnings, what we did not know about Paris traceroute, and as well as the wonderful implementation of FB tracer. We learned a lot about it during the hack. We would have loved to get more time and be able to do more justice to it, but and we also learned about the various exception traffic and the flows which we can utilize and minimize the kind of impact which we regularly see in our networks. So to conclude, it's always like we try to get the requisite data. Concurrency remains an issue. As we scale, it's difficult to run a centralized service which can fetch data as we need. So, and we also try to do some part of like route dampening, basically ensuring that we drain the traffic which we do not want to go through the link, and use alternative form of some traffic. Our code is available on the link which has been indicated. And with that, thank you so much.
Do we have any questions for any of our teams? Okay, so thank you, Matt, and thank you, winning teams.